Imagine for a moment that you are standing outside on a clear night, looking up at the stars. The air is still. The sky is vast. You feel small, maybe even insignificant, but also somehow connected to something enormous and ancient. Now imagine that at this very second, invisible to every instrument you own, invisible to your eyes, invisible to every camera ever built, a storm is passing through your body. Not around you, not above you, through you, right now. Billions upon billions of particles, each one carrying mass, each one shaped by gravity, each one a fragment of something that makes up more than a quarter of everything that exists in the universe, are streaming through your flesh and bone at incredible speed, and you feel absolutely nothing. You cannot detect them. You cannot stop them. You cannot even prove they are there with any tools sitting in your home. And yet some of the most brilliant physicists alive today believe this is happening. Not as a metaphor, not as science fiction, as a real, measurable, potentially confirmable physical phenomenon occurring at this very moment as you listen to these words. Welcome to one of the most extraordinary stories in the history of science. A story about something called a dark matter hurricane. A story about an invisible river of unknown particles that may be flowing through our solar system right now. A cosmic stream of darkness moving at nearly 500 kilometers per second, the remnants of a galaxy that our own Milky Way devoured billions of years ago. A story that connects ancient cosmic violence to the present moment. A story that just might, change everything we thought we knew about the nature of matter, the structure of the universe, and our place within it. A story that starts not in a laboratory, but in the wreckage of a galactic collision that happened before our planet even existed. But before we can understand what a dark matter hurricane is, we have to understand what dark matter is. And to understand what dark matter is, we have to confront one of the most uncomfortable truths in all of modern science. A truth that physicists have known for decades, but that still has the power to stop you cold if you really let it sink in. Ready? Here it is. We do not know what most of the universe is made of. Not approximately. Not with some caveats. We genuinely, fundamentally, deeply do not know. Everything you have ever seen, touched, tasted, smelled, or measured. Every mountain and ocean. Every star in every galaxy. Every atom in every molecule. Every particle ever detected in every accelerator ever built. All of it, all of the visible, tangible, measurable matter in the universe, accounts for only about 5% of what the universe actually contains. 5%. The remaining 95% is divided between something called dark energy, which accounts for roughly 68% and appears to be driving the accelerating expansion of the universe, and something called dark matter, which accounts for approximately 27% and appears to be holding galaxies together. And we have no idea, in any fundamental sense, what either of those things actually is. Think about that for a moment. Pause right there and really let it settle. If everything humans have ever discovered, everything we have built our physics on, every equation, every model, every experiment, represents only 5% of reality, what does that say about how much we still have to learn? What does that say about the universe we think we live in? It is as if you spent your entire life studying the surface of a single pebble, convinced you were becoming an expert on geology, only to look up one day and realize you were sitting in the middle of the Himalayas. The story of dark matter does not begin with particle accelerators or underground detectors. It begins with a woman and a galaxy and a problem that would not go away. Her name was Vera Rubin. She was born in 1928 in Philadelphia, and from childhood she was obsessed with the stars. She would lie in her bedroom watching the sky rotate through her window and feel something she could not quite name, a pull, a certainty that the universe had secrets worth spending a lifetime chasing. She was right. But the world she grew up in did not make the chase easy. When she applied to Princeton to study astronomy, she was told they did not accept women in the graduate program. This was not ancient history. This was the 1940s. She went to Cornell instead, then to Georgetown, and she built her career with a kind of quiet, relentless determination that history tends to underestimate until it cannot be ignored anymore. In the 1960s and 1970s, Vera Rubin was working with astronomer Kent Ford, and together they were measuring something called galactic rotation curves. Here is what that means. When a galaxy spins, the stars inside it orbit the galactic center, much like planets orbit the sun. Based on everything we understood about gravity at the time, based on Newton, based on Einstein, based on every verified equation in our arsenal, the stars at the outer edges of a galaxy should be moving more slowly than the stars closer to the center. This is exactly what happens in our solar system. Mercury, close to the Sun, moves at about 47 kilometers per second. Neptune, far from the Sun, moves at only about 5 kilometers per second. Gravity weakens with distance, and so orbital speeds fall off as you move outward. This is basic physics. This is settled, verified, uncontroversial physics. Except that when Vera Rubin and Kent Ford looked at real galaxies, that is not what they found. At all. The stars at the outer edges of galaxies were moving just as fast as the stars near the center. Sometimes faster. The rotation curves were flat when they should have been declining. It was as if Neptune were moving at the same speed as Mercury. It was as if the outer regions of galaxies were being held by gravity that was not there, by mass that did not exist, by something invisible. Vera Rubin was careful and methodical. She did not rush to dramatic conclusions. She and Ford measured dozens of galaxies, then hundreds. Every single one showed the same pattern. Every single one had a rotation curve that refused to drop off. The implications were unavoidable. There had to be mass that was not emitting light, not reflecting light, not interacting with light at all, and yet still exerting gravitational pull on everything around it. There had to be a vast, invisible halo of some kind of matter surrounding every galaxy, extending far beyond the visible stars, holding the whole structure together like a cosmic skeleton that no one could see. Now, to be fair to history, Vera Rubin was not the first person to notice that something was off. As far back as 1933, a Swiss astronomer named Fritz Zwicky had observed something strange about the Coma Cluster, a massive collection of galaxies held together by gravity. He calculated how much mass would be needed to keep all those galaxies from flying apart given how fast they were moving, and the number he got was hundreds of times greater than the mass of all the visible galaxies combined. He called this missing mass Dunkel Materie, which is German for dark matter. But Zwicky was famously abrasive, often wrong about other things, and his idea was not taken seriously for decades. It was Vera Rubin's meticulous, repeated, undeniable data that finally forced the scientific community to confront the reality that something enormous and invisible was shaping the universe. Ask yourself this right now. If there is an entire category of matter that makes up 27% of the universe, that surrounds every galaxy including our own, that has been affecting the structure of the cosmos since the very beginning, how is it possible that we have never directly detected a single particle of it? How can something that massive, that influential, that everywhere, be completely invisible to every instrument we have built? Does that possibility make you feel excited? Or does it make you feel something closer to unease? The answer to why we have not detected dark matter yet gets into some of the deepest and most contentious territory in modern physics. The leading candidate for what dark matter might be is a type of particle called a weakly interacting massive particle, or WIMP. The name tells you almost everything you need to know about why it is so hard to find. The word massive here does not mean enormous in size. It means the particle has mass, which is significant because a lot of particles, like photons, the particles that make up light, have no mass at all. WIMPs would be relatively heavy particles, possibly somewhere between 10 and 1,000 times the mass of a proton. But the crucial word is weakly. WIMPs, if they exist, interact with normal matter only through gravity and possibly through the weak nuclear force, one of the 4 fundamental forces of nature. They do not interact through electromagnetism. They do not absorb or emit light. They do not reflect photons. They are, for all practical purposes, ghosts. They pass through ordinary matter the way sunlight passes through glass, but with even less interaction. This means that if a WIMP were to pass through your hand right now, there would be no effect. If 100 billion WIMPs were to pass through a mountain of lead, almost none of them would leave any trace. To detect these particles, scientists have built some of the most extraordinary and sensitive instruments in human history. They have gone deep underground, beneath miles of rock, to shield their detectors from cosmic rays and other background radiation. They have built tanks filled with liquid xenon and surrounded them with sensors so sensitive they can detect single photons. They have cooled germanium crystals to temperatures colder than outer space and listen for the faint vibration that a single WIMP collision might produce. They have been doing this for decades, at facilities like the Large Underground Xenon Experiment in South Dakota, at the Xenon 1T detector beneath the Gran Sasso Mountain in Italy, at the Pandex experiment in China, and at many other underground laboratories around the world. And so far, they have found nothing. Or more precisely, they have found nothing that definitively confirms the existence of WIMPs. The detectors have gotten so sensitive that they are now probing regions of physics that theorists predicted WIMPs should occupy, and the silence is becoming deafening. Some physicists are beginning to wonder if WIMPs are the wrong answer. Maybe dark matter is something else entirely. Maybe it is made of axions, hypothetical particles originally proposed to solve a different problem in physics entirely. Maybe it is made of sterile neutrinos. Maybe it is made of something no one has thought of yet. Maybe, and this is the most unsettling possibility of all, maybe dark matter does not interact with anything except gravity, in which case we may never be able to detect it in a laboratory no matter how sensitive our instruments become. But here is where the story takes a remarkable turn. Here is where the cosmic becomes personal. Here is where an event that happened billions of years ago in the darkness between galaxies begins to matter for us right now, at this moment, on this planet, in this solar system. Because some physicists believe that if we want to find dark matter, we should stop thinking about it as a uniform, static background and start thinking about it as a dynamic, flowing structure. And if dark matter flows, then maybe, just maybe, we are inside one of its currents right now. To understand this, you need to know about something called the stellar stream. Galaxies are not eternal, unchanging things. They are dynamic, violent, constantly evolving objects. When two galaxies come close enough to each other, gravity does something extraordinary. It pulls them apart and smears their stars across space in long, thin ribbons, like taffy being stretched between two hands. These ribbons are called stellar streams. They are the ghost trails of galaxies that have been torn apart, their stars and gas and dark matter halos shredded and scattered across thousands of light years. Our Milky Way is surrounded by dozens of these streams, the remnants of smaller galaxies and globular clusters that got too close and were consumed, stretched into long arcs of stars that wrap around our galaxy like ribbons around a gift. One of the most significant of these streams was identified in 2018 by a team of astronomers analyzing data from the European Space Agency's Gaia satellite. The Gaia satellite is one of the most ambitious astronomical projects ever undertaken. Its mission is to precisely map the positions and movements of over 1 billion stars in the Milky Way, creating the most detailed three-dimensional map of our galaxy ever assembled. And when scientists started digging through the Gaia data, they found something astonishing. A group of stars in our galactic neighborhood, hundreds of thousands of them, all moving in the same direction, all sharing the same origin, all streaming together in a coherent flow through our local region of space. They named this stream the S1 stream, and they traced it back to what appeared to be a dwarf galaxy, a small satellite galaxy of the Milky Way that was cannibalized by our own galaxy roughly billions of years ago. The Milky Way had eaten another galaxy, and the shredded remains were flowing past us right now, right here, in our own galactic backyard. The researchers who published this finding, Kieran O'Hare, Christopher McCabe, and their collaborators, calculated the properties of this stream with remarkable precision. The S1 stream, they determined, is passing through our solar system at a speed of approximately 470 kilometers per second relative to the Sun. That is not a typo. 470 kilometers per second. For comparison, The International Space Station orbits Earth at about 7.7 kilometers per second. A bullet from a high-powered rifle travels at roughly 1 kilometer per second. The Voyager 1 spacecraft, the fastest human-made object ever launched, is traveling at about 17 kilometers per second. The S1 stream is moving at 470 kilometers per second. It is not just fast by human standards. It is fast by cosmic standards. And the direction it is moving, almost directly at us, toward the solar system, pouring through our local region of space right now. Now here is the crucial connection that turns this from an interesting astronomical observation into something that could potentially change the course of dark matter research. When that dwarf galaxy was torn apart by the Milky Way, it did not lose just its stars. Stars are only the visible, luminous component of any galaxy. Galaxies are surrounded by massive dark matter halos, and when the dwarf galaxy was disrupted, its dark matter halo was disrupted too. The dark matter that had surrounded that galaxy was also stretched and scattered, shredded into a stream along with the stars. And if the stars of that disrupted galaxy are now streaming through our solar system at 470 kilometers per second, then the dark matter of that galaxy should be streaming through our solar system at the same speed, in the same direction. This is what physicists mean when they talk about a dark matter hurricane. It is not a hurricane of dark matter in the sense of a swirling storm. It is a hurricane in the sense of a fast, powerful, directional wind. A stream of dark matter particles flowing through our solar system at extraordinary speed, much faster than the average speed of dark matter particles in the normal galactic dark matter halo. And this matters enormously for dark matter detection, because the energy that a dark matter particle deposits in a detector when it collides with an atomic nucleus depends critically on how fast the particle is moving. Faster particles carry more energy, and particles moving at 470 kilometers per second carry a lot more energy than the typical dark matter particle drifting through the galactic halo at more typical speeds. If the S1 stream is real, and if dark matter is made of particles that can occasionally interact with ordinary matter, then the dark matter in the S1 stream should be hitting atomic nuclei in our detectors with enough force to potentially cross detection thresholds that the ordinary galactic dark matter background falls below. This is not speculation for speculation's sake. The O'Hare et al. Paper, published in the journal Physical Review D in 2018, was a serious, peer-reviewed scientific analysis that calculated in quantitative detail what effect the S1 stream would have on different types of dark matter experiments. And the results were both exciting and nuanced. For WIMPs above a certain mass threshold, the S1 stream could significantly boost detection rates in existing experiments. For lighter dark matter candidates, like axions, the boost could be even more dramatic because lighter particles are more sensitive to the directional information encoded in a fast-moving stream. But let us take a step back here, because there is something important to understand about how all of this connects to the larger picture. The search for dark matter is not just a technical problem. It is one of the defining intellectual adventures of our time, and it is being pursued by thousands of scientists around the world with extraordinary creativity, dedication, and increasingly sophisticated tools. And it is happening against a backdrop of genuine uncertainty, of real scientific debate, of competing theories and surprising findings that shift the landscape constantly. The story of the S1 stream and the dark matter hurricane is not just a story about one discovery. It is a window into the entire enterprise of trying to understand what the universe is made of. It is a story about how science works at the frontier, how it builds on the work of previous generations, how unexpected observations from one field can suddenly become crucial for questions in a completely different field, and how a single piece of data, like the Gaia satellite stellar maps, can open doors that seem permanently closed. So let us go deeper. Let us talk about the Milky Way itself, because to understand dark matter hurricanes, you need to understand something about the kind of galaxy we live in, and about the violent history that has shaped everything around us. The Milky Way is a barred spiral galaxy, which means it has a central bar-shaped structure made of stars, with spiral arms extending outward from the ends of that bar. It is roughly 100,000 light-years across and contains somewhere between 100 and 400 billion stars. Our Sun is located on one of those spiral arms, the Orion Arm, about 26,000 light-years from the galactic center. We orbit the center of the galaxy at a speed of about 220 kilometers per second, completing one orbit every 225 to 250 million years. The last time the Sun was in the position it currently occupies, dinosaurs were just beginning to appear on Earth. But the Milky Way we see today is not the Milky Way as it has always been. Our galaxy has a violent history. It has grown to its current size by consuming smaller galaxies over billions of years, pulling them in with its massive gravitational field, tearing them apart, and incorporating their stars and gas and dark matter into its own structure. This process, called galactic cannibalism, is not unusual. It is actually how most large galaxies grow. And the evidence for this history is written in the streams of stars that now wrap around our galaxy, the ghost trails of the galaxies that came before and were absorbed. The Sagittarius dwarf galaxy is perhaps the most famous example. Discovered in 1994, it is a small elliptical galaxy currently being devoured by the Milky Way. Its stars have been stretched into a massive stream that wraps around the Milky Way multiple times, creating a vast arc of stars that has been traced across large portions of the sky. Some of those stars are relatively close to us. The process of disruption is still ongoing. The Sagittarius dwarf is being actively consumed as we speak, and its shredded remains are winding through our galaxy like a long scarf unraveling in the wind. The dwarf galaxy that gave rise to the S1 stream suffered a similar fate, but much earlier. The stars of this long-dead galaxy are now flowing through our local neighborhood, visible to the Gaia satellite as a coherent kinematic group. Stars that share the same velocity, the same direction, the same origin, even though they are now distributed across large regions of space. They are the survivors of an ancient galactic murder, witnesses to a catastrophe that happened so long ago that our Sun and Earth did not yet exist when it began. Here is a question worth sitting with. If entire galaxies can be torn apart and absorbed by larger ones, if the universe is this violent and this dynamic on cosmic timescales, what does that say about permanence? What does it say about the idea that any structure, any order, any arrangement of matter in the universe is truly stable? On the timescales of the cosmos, everything is temporary. Everything is in motion. Everything is subject to the overwhelming, indifferent, beautiful force of gravity. Does that thought disturb you, or does it fill you with something like wonder? Now let us talk about the specific findings of the O'Hare et al. paper in more detail, because the science here is genuinely fascinating and the implications are profound. The team used Gaia data to identify the S1 stream by looking for stars with similar velocities moving in a coherent direction relative to the Sun. They found approximately 30,000 stars that could be associated with the stream. Using the properties of these stars, including their velocities, their positions, and their chemical compositions, they were able to reconstruct the properties of the original dwarf galaxy and the stream itself with considerable accuracy. What they found was that the S1 stream is currently moving through our solar system in a very specific direction, roughly toward us from the direction of the constellation VOID, and at that extraordinary speed of around 470 kilometers per second. They then calculated what effect this stream would have on dark matter detectors if dark matter is indeed flowing through our region of space along with the stars. For WIMP detectors, the boost is significant but depends heavily on the mass of the WIMP and the type of detector. For WIMPs above about 10 GeV in mass, the S1 stream enhances detection rates by creating a high-energy tail in the recoil spectrum, a population of events at higher energies than would be expected from the ordinary galactic dark matter background. This is important because existing detectors like Xenon 1T and LUX Zeppelin are already sensitive to this mass range, which means that if WIMPs exist and if the S1 stream's dark matter content is at the expected level, we should be seeing some signal enhancement. The fact that we have not definitively seen such enhancement could mean that WIMPs are lighter or heavier than expected, or that the stream's dark matter content is lower than estimated, or that dark matter does not interact with ordinary matter in the way WIMPs are expected to. But here is where it gets really interesting. For axion dark matter, the S1 stream has potentially even more dramatic implications. Axions are hypothetical particles that were originally proposed in 1977 by physicists Roberto Pecchiai and Helen Quinn to solve an unrelated problem in particle physics called the strong CP problem. The strong CP problem is a puzzle about why the strong nuclear force, which governs the behavior of quarks and protons and neutrons inside atomic nuclei, does not seem to violate a symmetry called CP symmetry the way the theory predicts it should. Pecchiai and Quinn proposed a new symmetry of nature that, when broken, would produce a new particle. Frank Wilczek, who later won the Nobel Prize in Physics for completely unrelated work, named this particle the axion after a brand of laundry detergent because it cleaned up the CP problem in the theory. The axion, if it exists, would be an extremely light particle, perhaps billions or trillions of times lighter than an electron. It would be weakly interacting like WIMPs, but its interactions would be of a different type, primarily through its coupling to photons. Under the right conditions, an axion can convert into a photon, and this is the basis for most proposed axion detection experiments. The most developed of these is the axion haloscope, a device that uses a powerful magnetic field and a resonant microwave cavity to coax axions into converting into detectable photons. The Axion Dark Matter Experiment, or ADMX, at the University of Washington has been operating one of the most sensitive axion detectors ever built, and it has been systematically searching through different possible axion mass ranges with increasingly impressive sensitivity. Now here is why the S1 stream matters for axion searches. In a typical axion haloscope, the signal depends not just on whether axions exist but on the flux of axions passing through the detector and their velocity distribution. A fast-moving stream of axions from the S1 stream would produce a signal with a very specific frequency, a narrow peak in the microwave spectrum that would be offset from the frequency expected from the slow-moving galactic halo axions. This frequency offset is directly related to the stream's velocity, and because the S1 stream has such a high and well-determined velocity, any axions it contains would produce a signal at a very specific, calculable frequency that astronomers can predict in advance. If that peak were found, it would be, as the O'Hare paper puts it, a smoking gun for both the existence of axion dark matter and the reality of the S1 stream's dark matter component. The implications of this are staggering. It means that an astronomical observation, the discovery of a stellar stream by a satellite designed to map star positions, could directly guide laboratory experiments in particle physics. It means that the cosmos and the laboratory are more deeply connected than we sometimes appreciate. It means that the universe itself is providing us with a natural accelerator, a dark matter beam, aimed right at our detectors. But let us not get too far ahead of ourselves. There are important caveats and uncertainties here. The most important one is this. We know the S1 stream exists as a stellar stream. We can see the stars. We can measure their velocities. We can reconstruct their origins. But we cannot directly measure the dark matter content of the stream. Stars and dark matter were associated in the original dwarf galaxy, but the disruption process does not necessarily maintain that association perfectly. Dark matter particles interact only gravitationally, which means they respond differently to the tidal forces of galactic disruption than stars do. Simulations suggest that the dark matter associated with a disrupted dwarf galaxy does tend to form streams in the same direction as the stellar streams, but the density and velocity structure of the dark matter stream may be different from the stellar stream in ways that are hard to predict precisely. This uncertainty means that the enhancement of detection rates expected from the S1 stream could be larger or smaller than the estimates in the O'Hare paper by a significant factor. It is also possible, if unlikely, that the dark matter from the original dwarf galaxy was stripped away and dispersed more thoroughly than the stellar stream suggests, leaving a lower density or more diffuse dark matter remnant. The truth is, we will only know what the dark matter component of the S1 stream looks like when we either detect it or constrain it in dark matter experiments. And this is actually a powerful argument for why the experiments are important. They are not just searching blindly. They have a target, a predicted stream with specific properties that can be tested. There is another fascinating layer to this story that involves the question of how many such streams might be passing through our solar system. The S1 stream is not the only stellar stream in the Milky Way. There are dozens of known streams, some associated with disrupted globular clusters, some with disrupted dwarf galaxies, some with more complex merging events. Some of these streams may also pass through our solar system. The Gaia satellite continues to reveal new streams with every data release, and the full picture of our galaxy's merger history is still being assembled. In 2019, researchers announced the discovery of what may be the biggest merger event in the Milky Way's history, an ancient collision with a massive dwarf galaxy that astronomers nicknamed Gaia Sausage Enceladus, or GSE. This galaxy, which appears to have merged with the Milky Way roughly 8 to 10 billion years ago, was so large that it fundamentally reshaped our galaxy's inner structure. The stars from this ancient collision make up a large component of what astronomers call the interstellar halo of the Milky Way, the spherical distribution of old stars that surrounds the disk. And because this merger was so massive and so ancient, its dark matter debris has likely been thoroughly mixed into the background dark matter halo of our galaxy. But some components of this merger's debris may still form identifiable structures in velocity space, coherent groups of stars and dark matter particles moving in similar directions that could affect dark matter detection experiments in ways we are still working out. The picture that is emerging from all of this research is one of extraordinary complexity and beauty. Our galaxy is not a smooth, uniform structure. It is a layered, complicated, dynamically rich object that has been built up over billions of years through countless mergers and disruptions. The dark matter in our galactic neighborhood is not uniformly distributed. It is lumpy, streamy, directional. It has a complicated velocity structure that reflects the entire history of our galaxy's formation. And navigating that complexity, understanding it well enough to use it to guide dark matter searches, is one of the great intellectual challenges of contemporary astrophysics. Now let us step back and think about what we are really asking when we ask whether we are passing through a dark matter hurricane right now. This is not just a question about whether certain particles exist. It is a question about whether we can read the universe's history in the structure of the invisible world around us. It is a question about whether ancient cosmic events, mergers of galaxies billions of years ago, can leave traces that we can detect in our laboratories today. It is a question about the depth of the connections between cosmology and particle physics, between the largest scales of the universe and the smallest. And it is a question with real urgency, because the next generation of dark matter experiments is being designed right now. The LUX Zeppelin detector, which began operating in 2022 at the Sanford Underground Research Facility in South Dakota, is the most sensitive WIMP detector ever built, using 10 tons of liquid xenon to search for the faint signatures of dark matter particle collisions. The Xenon NT experiment at Gran Sasso is similarly pushing the boundaries of sensitivity. The ADMX experiment is systematically scanning axion masses with unprecedented precision. Super CDMS, the Super Cryogenic Dark Matter Search, is operating cryogenic detectors in the deep underground laboratory at SNOLAB in Canada. And next-generation experiments being planned, like Darwin for WIMPs and Abracadabra for axions, promise sensitivities that were unimaginable a decade ago. All of these experiments benefit from the kind of astrophysical guidance that the S1 stream provides. If we know there is a high-velocity stream of dark matter flowing through our solar system in a specific direction at a specific speed, we can tune our detectors to be maximally sensitive to that signal. We can look for the specific spectral and directional signatures that such a stream would produce. We are not hunting completely in the dark. We have a map, even if it is drawn in stars rather than in the particles we are really looking for. Here is something to consider. The fact that stellar streams exist, that galaxies have been disrupted and their remains scattered across space, is itself a profound statement about the nature of dark matter. The fact that stellar streams are coherent, that the stars in them have maintained similar velocities over billions of years of galactic evolution, tells us that the dark matter halo of our galaxy is relatively smooth on the scales relevant for these streams. If the dark matter halo were too lumpy or too granular on small scales, it would have disrupted the coherence of the stellar streams through gravitational scattering long ago. The persistence of stellar streams is actually evidence about the properties of dark matter, evidence that it is, at least on the relevant scales, relatively cold and smooth. This connects to one of the major debates in dark matter theory, the question of whether dark matter is cold or warm or hot. Cold dark matter consists of particles that were moving slowly when the first structures in the universe formed. Warm dark matter consists of particles that were moving at intermediate speeds. Hot dark matter consists of particles that were moving relativistically, close to the speed of light, when structure formation began. The distinction matters enormously for the large-scale structure of the universe, because fast-moving particles would have smoothed out small-scale density fluctuations, preventing the formation of small structures like dwarf galaxies. Cold dark matter, on the other hand, predicts a universe full of small-scale structure, a rich zoo of small halos and subhalos and streams. And the universe we observe is broadly consistent with the cold dark matter picture, though there are some tensions and puzzles at small scales that are still being worked out. The existence of the S1 stream and other stellar streams is part of this larger story about the nature of dark matter. Streams form when dark matter halos are small enough and coherent enough to maintain their identity over long periods of galactic evolution. The structure of the streams tells us something about the fundamental properties of dark matter particles. It is a kind of dark matter spectroscopy, using the shapes and properties of cosmic structures to infer the physical characteristics of particles we cannot directly see. But wait, there is another angle to this story that we have not yet explored, and it is perhaps the most philosophically profound one of all. It concerns the question of what it would mean if we actually found the dark matter stream. Not just detected a signal that might be consistent with the stream, but confirmed it beyond any reasonable doubt. What would that discovery do to our understanding of the universe, of ourselves, of our place in the cosmos? Think about the history of discoveries that have shifted human self-understanding. Copernicus showing that the Earth orbits the Sun, not the other way around, displaced us from the center of the solar system. Darwin showing that humans share common ancestors with all other life on Earth, displaced us from a position of special creation. Hubble showing that the Milky Way is just one of billions of galaxies displaced us from a central position in the cosmos. Each of these discoveries was not just a piece of scientific information. Each was a fundamental revision of humanity's place in the universe. And in each case, the initial resistance was enormous, because these discoveries challenged deeply held assumptions about what was special, what was central, what was important. A confirmed detection of dark matter would be a discovery of comparable magnitude. It would not just tell us what 27% of the universe is made of. It would begin to answer questions that have been sitting at the heart of physics and cosmology for half a century. Why does the universe have the structure it has? How did galaxies and galaxy clusters form? What was the early universe like? Are there other forces and particles beyond the ones we know? Is the standard model of particle physics, our current best description of the fundamental particles and forces, complete, or is it just the tip of an iceberg of physical reality that extends far beyond our current knowledge? And if the detection came from the S1 stream specifically, if the dark matter signal were found to have exactly the velocity and direction predicted from the stellar stream observations, that would be a triumph of a very specific kind. It would mean that we solved the dark matter problem not by building ever larger particle accelerators or ever more sensitive laboratory detectors in isolation, but by listening to what the cosmos itself was telling us, by reading the history of galactic mergers in the structure of the dark matter flowing through our solar system right now. It would mean that the universe was, in a sense, trying to reveal itself to us, and we finally figured out how to listen. Of course, there is also the possibility, which we should acknowledge honestly, that the story does not end this way. The search for dark matter has been going on for decades, and the universe has not yet yielded its secret. Each generation of experiments has improved sensitivity by orders of magnitude. Each new generation of detectors has probed deeper into the theoretical space where dark matter was expected to be found. And so far, the silence continues. Maybe dark matter is real but does not interact with ordinary matter in any way we can currently detect. Maybe the solution to the galactic rotation curve problem is not dark matter at all, but a modification of gravity. Maybe there are multiple components of dark matter, some detectable and some not. The mystery is genuine, and the honest answer to many of these questions is still we do not know. But the S1 stream represents something new in this long search. It represents a moment when the astrophysical evidence pointed to a specific, concrete prediction that can be tested in the laboratory. And that is the kind of bridge between theory and experiment that drives science forward. Even if the search comes up empty, the constraints that experiments can place on the dark matter content of the S1 stream will tell us something important. And even if the stream's dark matter component turns out to be smaller or different from what we expect, the methodology of using astrophysical structures to guide laboratory searches is here to stay. The Gaia satellite has revealed that our galaxy is far more complex and interesting than we knew. Future surveys will reveal even more. And every new stream, every new merger remnant, every new piece of our galaxy's history that we uncover adds another entry to the catalog of potential dark matter targets. Let us pause here and ask another question that might sound simple but is actually quite deep. How do we know the S1 stream is real? We cannot see dark matter. We can see the stars in the stream, but how do we know those stars all came from the same original dwarf galaxy? How do we know they are genuinely moving together and not just appearing to do so by coincidence? The answer involves a beautiful piece of celestial mechanics called the conservation of integrals of motion. When a galaxy is being disrupted by tidal forces, its stars are peeled off gradually. But even though the stars end up spread across enormous regions of space, they conserve certain mathematical quantities related to their orbits. Energy and angular momentum, for example, are approximately conserved for stars moving in a slowly changing gravitational potential. This means that even after a dwarf galaxy has been shredded and its stars scattered across thousands of light years, those stars still share similar values of energy and angular momentum, similar orbital characteristics, that betray their common origin. By looking at these conserved quantities in the Gaia data, astronomers can identify groups of stars that travel together even when they are now spatially separated. It is like recognizing members of a family by their shared features even after they have moved to different cities. The S1 stream was identified using exactly this method. The stars in the stream share a common velocity vector that points back to a coherent origin. Their chemical compositions, their ratios of different elements like iron, magnesium, and calcium, are consistent with a common stellar population that evolved in a smaller galaxy with a different chemical enrichment history than the Milky Way. Multiple independent analyses have confirmed the reality of the stream. It is one of the best characterized stellar streams in our local galactic neighborhood. But even granting all of this, you might still wonder, how confident are we that the dark matter associated with the original dwarf galaxy is still flowing in a coherent stream rather than having been dispersed into the background? This is actually a nuanced and actively researched question. The short answer is that numerical simulations of galaxy mergers suggest that dark matter does form streams following galaxy disruption. But the dark matter streams are typically broader and more diffuse than the stellar streams because dark matter does not have the same orbital dynamics as stars once the originating galaxy has been disrupted. Stars can be lost from a galaxy only at specific points in the orbit, called tidal tails, while dark matter can be dispersed more continuously. This tends to make dark matter streams broader in velocity space, which means the signal in a dark matter detector would be spread over a wider range of energies, which in turn makes it harder to detect above the background. However, the key insight from the O'Hare et al. Paper is that even a diffuse dark matter stream moving at the specific velocity of the S1 stream would produce a detectable signature if the experiments are sensitive enough, because the velocity of the stream is so much higher than typical galactic dark matter velocities. The high speed is the key. It means the signal appears in a part of parameter space where the background is relatively low, making it easier to distinguish from noise. There is also an interesting and somewhat poetic aspect to the geometry of the situation. The S1 stream is moving almost directly toward us from a specific direction in the sky. This means that if you are sitting in a detector on Earth, the dark matter particles from the stream are coming at you from a specific direction, hitting your detector preferentially from one side rather than uniformly from all directions. This directional information is a potential goldmine for detection. If you had a detector that could measure not just the energy of a nuclear recoil, but also the direction from which the striking dark matter particle came, you could compare the direction of events in your detector with the predicted direction of the S1 stream and look for a match. This is the idea behind directional dark matter detection, an approach that has been proposed for years but has been technically challenging to implement. Some experiments, like DRIFT in the United Kingdom and NEWAGE in Japan, have been working on direction-sensitive detectors. The idea is to use a gas-filled detector in which a nuclear recoil from a dark matter particle collision would produce a track in the gas rather than just a point-like signal, allowing the detector to determine the direction from which the particle came. The challenge is that gas detectors tend to be less sensitive than liquid xenon detectors because they contain far less target material, and the dark matter signal is already incredibly rare even in the best liquid xenon detectors. But here is an important point. The S1 stream, if its dark matter component has the expected properties, could provide a uniquely strong motivation for directional detection. If we have a predicted direction and speed, and if we can build a directional detector sensitive enough to test that prediction, then we have a specific, targeted experiment with a clear yes or no outcome. This is very different from the current situation in most dark matter searches, where experiments are scanning enormous ranges of possible masses and interaction strengths with no specific target other than broad theoretical expectations. Think about what this means in practice. It means that the discovery of the S1 stream may have changed not just the strategy of dark matter searches, but the entire intellectual framing of the enterprise. Before stellar streams were understood as dark matter reservoirs, the search for dark matter was primarily a matter of building better and better detectors and scanning more and more of the mass coupling parameter space. After the realization that specific astrophysical structures like the S1 stream are passing through our solar system, the search becomes more targeted, more informed, more like hunting for a specific animal in a specific habitat rather than random sampling of an unknown wilderness. Now let us talk about some of the other extraordinary consequences that would follow from a confirmed detection of dark matter, and particularly from one connected to the S1 stream. One of the most fascinating would be the prospect of what physicists call dark matter astronomy. If we could detect dark matter particles from the S1 stream, measure their velocity distribution, understand their properties, we would have a new tool for studying the history and structure of our galaxy. We would be able to use dark matter detectors as telescopes, not of light but of dark matter, looking back through galactic history to read the record of ancient mergers in the velocities of invisible particles. This might sound impossibly science fictional, but it follows logically from what we already know. The stars in the S1 stream are themselves a record of the merger event that created them. Their velocities, positions, and chemical compositions tell us about the mass and orbital properties of the original dwarf galaxy, about when the merger happened, about how far from the galactic center it occurred. If we could also measure the properties of the dark matter in the stream, we would have additional information about the original galaxy, particularly about the structure of its dark matter halo, which determines how the disruption proceeded. Different dark matter particle properties, different masses and interaction cross-sections, would have left different imprints on the structure of the dark matter stream. By comparing the observed dark matter stream properties with predictions from simulations, we could in principle constrain the properties of dark matter particles directly from astronomical observations. This would be a completely new kind of science. It would combine particle physics, astrophysics, and cosmology in a way that is currently only possible in a limited sense. It would open up a new window on the early universe, when galaxy mergers were much more frequent and violent, and on the nature of dark matter itself. It would be, in a very real sense, the birth of dark matter astronomy. But even before we reach that point, even before we detect a single dark matter particle from the S1 stream, the stream is already teaching us things. The very fact that the stream exists and has the properties it does is evidence about the nature of dark matter. If dark matter were made of particles that interacted more strongly with ordinary matter, those interactions would have heated the dark matter in the original dwarf galaxy, changing the structure of its halo and affecting how the disruption proceeded and how the stream formed. The coherence and properties of the stellar streams we observe are actually constraints on dark matter properties, even without a direct detection. Similarly, The number, size, and properties of dwarf galaxies in the Milky Way's neighborhood are sensitive probes of dark matter physics. One of the most famous puzzles in cold dark matter cosmology is called the missing satellites problem. Simulations of galaxy formation in a universe filled with cold dark matter predict that a galaxy like the Milky Way should be surrounded by hundreds or even thousands of small satellite galaxies. But when astronomers look around our galaxy, they find only a few dozen known satellites. Where are the rest? Possible explanations include the idea that the missing satellites exist but are too faint or dark to have been detected yet, which may indeed be the case as sensitive surveys keep finding new ultra-faint dwarf galaxies, or the idea that some dark matter models suppress the formation of small halos in ways that standard cold dark matter does not. Each explanation carries different implications for dark matter physics, and stellar streams are part of the evidence base for sorting out these possibilities. Let us zoom out to an even larger picture for a moment. We have been talking about the S1 stream and the dark matter hurricane it may represent, but let us step back and think about what all of this tells us about the nature of the cosmos as a whole. The universe is approximately 13.8 billion years old. In its earliest moments, in the first fractions of a second after the Big Bang, it was an incredibly hot, dense, uniformly expanding soup of particles and radiation. The seeds of all the structures we see today, galaxies, clusters, filaments, and voids, were already present in tiny quantum fluctuations in the density of this primordial soup, fluctuations amplified by inflation into the density variations that gravity would later amplify into everything we see. Dark matter played a crucial role in this story. Because dark matter does not interact with light, it did not participate in the photon-baryon oscillations that characterized the early universe's sound waves, the same oscillations that left their imprint as the cosmic microwave background radiation. This meant that dark matter could start clumping under its own gravity earlier than ordinary matter could. It created the gravitational scaffolding, the dark matter halos, into which ordinary matter later fell, cooling and condensing into stars and galaxies. Without dark matter, the universe we see today would not exist. There would be no galaxies, no stars, no planets, no us. Dark matter is not just a mysterious component of the universe. It is the invisible architecture that made everything possible. And the S1 stream is a fragment of that architecture. It is a piece of the dark matter halo of a galaxy that formed billions of years ago, when the universe was young, when galaxy mergers were frequent and violent, when the large-scale structure of the cosmos was being assembled from smaller pieces. The stream flowing through our solar system right now carries the imprint of events that occurred before our sun was born, before Earth existed, before complex life had any chance to arise anywhere in this corner of the cosmos. When we talk about whether we are passing through a dark matter hurricane, we are talking about whether we are at this moment immersed in the remnants of an ancient cosmic event of extraordinary scale, flowing through a river of invisible matter that connects our present moment to the deep history of the universe. Is there anything more awe-inspiring than that? Or anything more humbling? We like to think of ourselves as being separate from the cosmos, looking up at it from a safe distance, studying it from the outside. But we are not outside. We are inside it. We are part of it. The dark matter stream is not something happening out there, somewhere in the distant universe. If it exists, it is happening here, in this room, in your body, in every atom of the planet beneath your feet. The cosmos is not something we observe. It is something we inhabit at every scale, from the quantum to the cosmic, and dark matter is part of the fabric of that cosmos whether we can detect it or not. Now let us talk about some of the specific experiments that are most likely to tell us whether the dark matter hurricane is real, and what we might learn from them in the next few years. Because this is not just history and theory. This is an ongoing, developing story with real discoveries potentially just around the corner. The LUX Zeppelin experiment, known as LZ, began its first physics run in 2022 and published its first results in 2023. With 10 tons of liquid xenon as its target material, it is currently the world's most sensitive WIMP detector. Its first results set new limits on the WIMP nucleon scattering cross-section across a wide range of WIMP masses, pushing the boundary of sensitivity significantly beyond previous experiments. But LZ is designed to run for many years and will continue to improve its sensitivity as it accumulates more data and reduces its backgrounds. The full dataset from LZ, expected over its planned 5-year run, will probe WIMP masses and interaction strengths that are approaching what theorists call the neutrino floor, the background of neutrinos from the sun and cosmic rays that begins to mimic the dark matter signal and will ultimately limit how deeply any liquid noble gas experiment can probe. If the S1 stream contains WIMPs above about 10 GeV in mass with interaction cross-sections near the current experimental limits, LZ might see it in its next few years of operation. The detection would appear as an excess of events at relatively high nuclear recoil energies, the specific energy range boosted by the stream's high velocity. And crucially, if the directional properties of the events could be analyzed, the excess would be concentrated in the part of the sky corresponding to the direction of the S1 stream, providing an additional confirmation. The Xenon-NT experiment, the latest in a long series of xenon-based detectors at the Gran Sasso National Laboratory in Italy, is LZ's main competitor in sensitivity. It uses approximately 8 tons of active xenon and has also published first results in recent years. Like LZ, Xenon-NT will spend the next several years probing the WIMP parameter space with increasing sensitivity. The two experiments are essentially in a race to be the first to either detect WIMPs or reach the neutrino floor, and the competition between them is one of the most exciting ongoing sagas in experimental physics. For Axion searches, the situation is different and in some ways more optimistic in the near term. ADMX has been systematically scanning axion masses in the range predicted by a class of models called QCD axions, the most theoretically motivated axion candidates, and it is now reaching sensitivities that can test realistic QCD axion models. If axions in the mass range ADMX is exploring exist, and if the S1 stream contains them, the stream might produce a detectable signal as a narrow peak in ADMX's output spectrum at a frequency corresponding to the stream's velocity. New experiments like Haystack at Yale and CAP in South Korea are also contributing to the axion search, using different technologies to cover different mass ranges and reach different sensitivity levels. There is also a fascinating new class of experiments called quantum sensors that may revolutionize dark matter detection in the coming decade. These experiments use the extraordinary sensitivity of quantum mechanical systems, things like superconducting qubits, atomic clocks, atom interferometers, and nuclear magnetic resonance sensors, to detect the tiny effects that dark matter particles might have on quantum systems. Because quantum systems can be sensitive to incredibly small perturbations, these approaches might be able to detect dark matter particles that are much lighter than WIMPs and axions, extending the search to a completely new region of parameter space. One particularly exciting example is the use of atom interferometry to search for ultralight dark matter. An atom interferometer works by splitting a quantum mechanical wave function of atoms along 2 different paths and then recombining them. The interference pattern at the recombination point depends on the phase accumulated along each path, and any difference in the gravitational or dark matter field between the 2 paths would show up as a shift in the interference pattern. If ultralight dark matter oscillates with a specific frequency, it would cause oscillating shifts in the interference pattern at that frequency. Experiments like MAGUS 100 in the United States and AION in the United Kingdom are being developed to search for exactly this kind of signal. Similarly, nuclear clocks that use the transitions of atomic nuclei rather than electron transitions like conventional atomic clocks, are being developed and could be sensitive to variations in fundamental constants caused by dark matter. If dark matter consists of ultralight particles that form a coherent oscillating field, the oscillation would cause temporal variations in things like the electron mass or the fine structure constant, which would show up as tiny oscillations in the ticking rate of atomic clocks. All of these techniques, from the brute force sensitivity of large liquid xenon tanks to the quantum precision of atomic clocks and interferometers, represent humanity's increasingly sophisticated assault on the dark matter mystery. And the discovery of the S1 stream and the concept of the dark matter hurricane adds a new dimension to all of them. Not just sensitivity, but direction. Not just mass, but velocity. Not just existence, but structure. Let us now think about the broader theoretical landscape and some of the alternative ideas that physicists have proposed to explain the galactic rotation curves and other evidence for dark matter. Because the story of dark matter is also a story about competing explanations and the criteria we use to evaluate them. Not everyone accepts the dark matter interpretation of the astrophysical evidence, though it must be said that the dark matter interpretation is overwhelmingly favored by the majority of cosmologists and particle physicists working in this field. The most developed alternative is called modified Newtonian dynamics, or MOND, proposed by Israeli physicist Mordechai Milgram in 1983. MOND proposes that Newton's law of gravity works differently at very low accelerations, specifically the accelerations characteristic of the outer parts of galaxies. Instead of the gravitational force falling off as the inverse square of distance, MOND proposes that at very low accelerations the force falls off more slowly, roughly as the inverse of distance rather than the inverse square. This simple modification turns out to explain the flat rotation curves of galaxies remarkably well, and it also successfully predicts a relationship between the mass of a galaxy and the speed of rotation in its outer regions called the Tully-Fisher relation. MOND has some genuine successes at the galactic scale, and these successes should not be dismissed. But it runs into serious difficulties at larger scales. It does not naturally explain the distribution of mass in galaxy clusters, which requires dark matter in amounts similar to those predicted by standard cosmology. It does not easily explain the cosmic microwave background, which encodes information about the early universe in a way that is beautifully fit by cold dark matter cosmology but is very difficult to reconcile with MOND. And it does not have a natural relativistic generalization that passes all the tests of general relativity, though various modified gravity theories have been proposed to try to fix this. Perhaps the most dramatic piece of evidence against MOND and in favor of dark matter is the bullet cluster, a system of two galaxy clusters that have collided with each other. When galaxy clusters collide, the hot gas that makes up the bulk of the ordinary matter in them is slowed down by electromagnetic interactions and piles up in the middle. But the dark matter halos, which interact only gravitationally, pass through each other without slowing down. The result is a spatial separation between the center of mass, which tracks the dark matter, and the center of light, which tracks the X-ray emitting gas. In the bullet cluster, observations with the Chandra X-ray Observatory and gravitational lensing measurements both confirm exactly this pattern. The center of mass is offset from the center of the gas in precisely the way expected if most of the mass is in dark matter halos that pass through each other. This observation is extremely difficult to explain with MOND without additional dark matter-like components, and it was widely seen as strong evidence for particle dark matter. More recent examples of similar cluster collisions have added to this evidence, though there have also been cases where the expected offset has not been as large as predicted, suggesting that some aspects of cluster dynamics are still not fully understood. The bullet cluster and its cousins are part of a larger body of evidence that collectively makes the case for particle dark matter very strong, even in the absence of a direct laboratory detection. There is also the evidence from the large-scale structure of the universe. When we look at the distribution of galaxies on the largest scales, we see that they are arranged in a cosmic web, a network of filaments and sheets separated by enormous voids, with galaxy clusters concentrated at the nodes where filaments intersect. This structure can be reproduced in computer simulations that include cold dark matter with remarkable accuracy. The simulations, which model the gravitational interactions of billions of dark matter particles along with the ordinary matter that forms galaxies, reproduce the observed large-scale structure in exquisite detail. Without dark matter, simulations cannot reproduce the observed cosmic web. And then there is the cosmic microwave background, the afterglow of the Big Bang, which encodes a snapshot of the universe when it was only about 380,000 years old. The tiny temperature fluctuations in the CMB, measured with extraordinary precision by satellites like WMAP and Planck, have a specific statistical structure, a pattern of peaks and troughs in what is called the power spectrum, that is sensitive to the amount and properties of dark matter in the early universe. The Planck satellite's measurements of the CMB precisely determine the total amount of dark matter, the amount of ordinary matter, and the cosmological constant, with impressive accuracy. The answer is consistent with what is needed to explain galactic rotation curves, the bullet cluster, and the large-scale structure of the universe. Dark matter is not a single observation explained away by a single alternative. It is a convergent evidence from multiple independent directions, all pointing to the same conclusion. So what exactly are we saying when we say we might be passing through a dark matter hurricane right now? We are saying this: if the dark matter paradigm is correct, and if the S1 stream carries dark matter in proportion to its stellar content, and if dark matter is made of particles like WIMPs or axions that can occasionally interact with ordinary matter, then right now, as you are reading or listening to these words, a vast river of dark matter particles is streaming through your body, through the Earth, through the entire solar system, at approximately 470 kilometers per second, carrying the invisible remnants of an ancient dwarf galaxy that was torn apart and consumed by the Milky Way billions of years before the Earth was born. This is the dark matter hurricane. It is not a metaphor. It is not a myth. It is a specific, quantitative, scientifically testable prediction based on real observations of stellar stream kinematics and real theoretical calculations of dark matter distribution. It is one of the most extraordinary ideas in contemporary physics, and it might be true. But there is one more layer to this story that we have not yet fully explored, and it may be the most profound of all. It concerns the question of what dark matter tells us about the deep structure of reality, and about the relationship between the known and the unknown in physics. Because dark matter, if it exists as particles, represents the first confirmed example of physics beyond the Standard Model, a new form of matter that does not fit into our current best theory of the fundamental constituents of nature. And that would be extraordinary, because the Standard Model, despite being incomplete in various ways, has been one of the most successful scientific theories in history. The Standard Model of particle physics was developed in the 1960s and 1970s and describes all the known fundamental particles and 3 of the 4 fundamental forces of nature. It predicted the existence of particles like the W and Z bosons, the gluon, and the Higgs boson, all of which were subsequently discovered in particle accelerator experiments. Its predictions have been verified to extraordinary precision. When physicists calculate the magnetic moment of the electron using the Standard Model, they get a result that agrees with experimental measurements to better than 1 part in a trillion. That is like measuring the distance from New York to Los Angeles to within a fraction of a millimeter. But the Standard Model does not include dark matter. It does not include gravity in a quantum mechanical framework. It does not explain why matter dominates over antimatter in the universe. It does not explain the masses of the neutrinos. And it does not explain dark energy. These are not small gaps. They are profound puzzles that tell us the Standard Model, despite its extraordinary successes, is not the final story. There is physics beyond it that we have not yet discovered. Dark matter is likely part of that beyond Standard Model physics. Whether it is WIMPs, which arise in supersymmetric extensions of the Standard Model, or axions, which arise in theories that address the strong CP problem, or something else entirely like extra-dimensional particles or asymmetric dark matter represents a doorway into a richer, deeper theory of nature. Finding it, measuring its properties, understanding how it fits into the larger picture of physics, would be a transformative achievement that would reshape our understanding of the fundamental constituents of reality. The dark matter hurricane, the S1 stream flowing through our solar system, is an opportunity. It is an opportunity to use the cosmos itself as a tool, to leverage the complexity and history of our galaxy to learn something that no particle accelerator has yet revealed. It is an invitation, written in the velocities of stars and the invisible mass of ancient galactic halos, to expand our understanding of what the universe is made of. And this brings us to something that rarely gets mentioned in the scientific papers, but is nonetheless essential to understanding why this discovery matters so much. The S1 stream is a reminder of how deeply connected everything in the universe is across time and space. The stars in the stream trace their origin to a galaxy that formed and evolved and lived and died billions of years ago. The dark matter those stars were associated with has been flowing through space ever since, maintaining a coherent direction, carrying the memory of its origin in the form of a specific velocity. And today, in this century, on this planet, with these instruments, we have the ability to detect it. We have the ability to receive a message from the deep past of the cosmos, written not in light but in invisible particles, transmitted across billions of years and billions of light years to arrive in our detectors at this precise moment in history. There is something deeply moving about that possibility. Something that connects science to the deepest human impulses, the desire to understand, to connect, to know where we came from and how we are related to everything else. The dark matter hurricane is not just a physics problem. It is a creation story. It is the universe telling us about its own history through the medium of invisible matter flowing through our world. Now let us talk about what other researchers have been saying about this, because the scientific community's response to the S1 stream discovery and its implications for dark matter detection has been rich and varied. The O'Hare et al. Paper was well received in the physics community and sparked considerable interest. Several subsequent papers built on its results, exploring the implications of the S1 stream and other stellar streams for specific dark matter detection experiments and specific dark matter models. Researchers at institutions from MIT to Oxford to CERN have been contributing to this discussion, and the topic has become a regular feature at dark matter conferences and workshops. One interesting subsequent development was a more detailed analysis of the dark matter velocity distribution in our local neighborhood, taking into account not just the S1 stream but also the known large-scale structure of the Milky Way and other identified stellar streams and merger remnants. This analysis produced what physicists call an empirical local velocity distribution for dark matter, a model of how dark matter particles in our neighborhood are moving that is based on actual astrophysical observations rather than simplified theoretical assumptions. This empirical distribution is more complex and more interesting than the simple Maxwellian distribution that is usually assumed in dark matter calculations, and it could change the interpretation of past and future experimental results. Another fascinating development involves what happens when you look at the S1 stream in the context of larger dark matter simulations. Researchers have compared the properties of the S1 stream with what is expected from numerical simulations of galaxy formation and dark matter evolution, and they find that streams like S1 are indeed expected in a universe filled with cold dark matter. The simulations predict that streams from disrupted dwarf galaxies should be a common feature of the local dark matter environment in galaxies like the Milky Way, not rare exceptions. This gives us more confidence that the dark matter in the S1 stream is real, even though we cannot directly detect it yet. There have also been interesting discussions in the community about the other stellar streams identified by Gaia and their potential contributions to the local dark matter environment. Each stream represents a different component of the local dark matter that may have a different velocity, direction, and density. The total local dark matter environment is therefore a superposition of many components. The smooth galactic halo, the debris from the major Gaia-Sausage-Enceladus merger, contributions from various stellar streams including S1, and possibly other components that have not yet been identified. Untangling all these components and understanding their individual contributions to the dark matter signal in a detector is a complex but tractable problem. One particularly interesting aspect of this discussion involves the question of dark matter substructure on small scales. In the standard cold dark matter paradigm, dark matter halos contain a huge number of smaller subhalos, gravitationally bound clumps of dark matter that were too small to attract enough ordinary matter to form visible galaxies. These subhalos, if they exist, might pass through the solar system occasionally, creating brief periods of locally enhanced dark matter density that could be detectable in long-running experiments. This is different from the smooth stream enhancement of the S1 stream, but adds another layer of interesting structure to the local dark matter environment. The possibility of dark matter subhalos passing through the solar system has been explored theoretically and connects to a fascinating and somewhat disturbing idea about the relationship between dark matter structure and life on Earth. Some researchers have speculated that the passage of dense dark matter clumps through the solar system could have gravitational effects on the Oort cloud, the distant reservoir of comets at the edge of our solar system. If a dense dark matter subhalo were to pass close enough to the solar system, its gravitational perturbation could perturb the Oort cloud and send a shower of comets into the inner solar system. This is highly speculative, as the density of dark matter subhalos passing through the solar neighborhood is expected to be quite low. But the idea raises the intriguing and somewhat unsettling possibility that dark matter might have influenced the history of life on Earth through its gravitational effects on comet trajectories. This is firmly in the realm of speculation rather than established science, and it is important to emphasize that. But it is the kind of speculation that illustrates how far-reaching the potential implications of dark matter can be. If dark matter is real, if it has structure, if it flows through our solar system in streams and clumps and voids, then it is not just a curiosity for physicists and cosmologists. It is a physical reality that shapes the environment we live in, even if its effects are so subtle that we have not yet been able to measure them. Let us now explore what it would feel like, emotionally and intellectually, to be a scientist working at the frontier of this search. What is it like to spend your career looking for something that might not interact with anything you have? What is it like to build an experiment of extraordinary sensitivity, lower the backgrounds to almost nothing, and then wait and listen and hear nothing? Is that failure, or is it progress? The physicists who work on dark matter detection are not naive. They know the history of their field, which is dotted with false alarms and near misses and results that look promising but could not be confirmed. The Dama/Libra experiment in Italy has been claiming a dark matter signal for over 2 decades, based on an annual modulation in their event rate that matches what is expected from the seasonal variation in the Earth's velocity through the galactic dark matter halo. But no other experiment has been able to confirm their result, and most physicists believe the Dama signal is due to an unidentified systematic effect rather than dark matter. The Cogent experiment also reported a possible modulation signal years ago that attracted attention before fading into uncertainty. The nature of science is that not every apparent signal survives scrutiny. The physicists working on Xenon 1T reported in 2020 an unexpected excess of electron recoil events, which briefly excited the community because it could in principle be interpreted as a signal from axions produced in the Sun or from other beyond standard model physics. But subsequent analysis showed the most likely explanation was a trace contamination of tritium in the xenon, a mundane background source rather than a new particle. Disappointing, yes, but instructive, because it showed how carefully these experiments must be understood before any claim of discovery can be made. The emotional reality of working in this field is one of sustained tension between hope and skepticism, between the excitement of possibility and the discipline of rigor. Every anomaly in a detector must be ruthlessly examined. Every background source must be identified and understood. Every systematic effect must be measured and controlled. The history of physics is full of cases where a mysterious signal turned out to be a known effect that was not properly accounted for, and the dark matter field takes this lesson seriously. The bar for a discovery claim is extremely high, and rightly so. But beneath the rigor and the caution, the excitement is real. The dark matter problem is one of the greatest open questions in science, and the possibility that we are on the verge of solving it, that the next generation of experiments might finally see what has been invisible for so long, is a genuine source of motivation and passion for thousands of researchers around the world. The dark matter hurricane, the S1 stream, is one piece of that motivation, a specific, astrophysically grounded target that gives the search a concrete direction and a testable prediction. Consider this image for a moment. Somewhere in the dark, underground, in a laboratory carved out of rock miles beneath a mountain, a tank of ultra-pure liquid xenon sits perfectly still. Sensors line its walls, each one listening for a single photon, the microscopic flash of light that would announce the collision of a dark matter particle with a xenon nucleus. Outside the tank, an elaborate system of shields blocks cosmic rays and radioactive backgrounds. The temperature is stable. The electronics are quiet. And through the rock and the shields and the xenon, particles are streaming. Neutrinos from the sun, thousands of billions of them every second. And perhaps, just perhaps, dark matter particles from the S1 stream, moving at 470 kilometers per second, carrying the memory of a galaxy that died before our sun was born. If one of those particles hits a xenon nucleus, the nucleus recoils. It moves a tiny bit. A few dozen electron volts of energy are deposited. The surrounding xenon scintillates, emitting a few dozen photons. The sensors pick up those photons. The electronics record a pulse. The data acquisition system stores the event. And somewhere, a physicist reviewing the data sees a signal. That is it. That is the entire interaction between an ancient galactic relic and a human instrument. A pulse of light lasting microseconds. A record in a computer. A number on a plot. And if it is real, if it is confirmed, if it repeats with the right statistical distribution, if it has the right energy in the right direction, if it passes every test that the skeptical scientific community can throw at it, then it becomes the most important discovery in the history of physics. Then it becomes confirmation that the universe is made of stuff we never knew existed, that dark matter is real, that the standard model is incomplete, that there is a new chapter to be written in the book of fundamental physics. The stakes could not be higher, and the patience required could not be greater. And the wonder at the possibility, the sense that we might be on the verge of something extraordinary, is part of what makes this one of the most captivating stories in all of science. Let us now talk about some of the things we might learn from dark matter that go beyond just knowing it exists. Because once we know what dark matter is made of, once we can measure its properties, the implications cascade in ways that are difficult to anticipate but almost certainly profound. If dark matter is made of WIMPs with a specific mass and interaction strength, that tells us something about what physics looks like at energies much higher than the ones we currently probe with particle accelerators. WIMPs are theoretically motivated by a concept called supersymmetry, which proposes that every known particle has a corresponding partner particle with different spin properties. Supersymmetry, if it exists, would solve several deep puzzles in the standard model and would naturally produce a WIMP dark matter candidate called the neutralino. But the Large Hadron Collider at CERN has been searching for evidence of supersymmetry for more than a decade and has so far found nothing. If WIMPs are discovered in dark matter detectors, it would provide indirect evidence for supersymmetry even in the absence of LHC signals, potentially pointing toward a version of supersymmetry with particles too heavy to be produced at current accelerator energies. If dark matter is made of axions, the implications are different and in some ways even more interesting. Axions are connected to a deep principle of symmetry in quantum field theory, and their discovery would confirm the Peccei-Quinn mechanism and explain why the strong nuclear force does not violate CP symmetry. But axions are also cosmologically important in a different way. If the axion is light enough, it could be produced in the early universe in a process called misalignment production, where the axion field starts at a non-zero value and oscillates around its minimum, producing a coherent condensate of axions that would constitute the dark matter. This is a very different production mechanism from the thermal relic mechanism expected for WIMPs, and it would have different implications for the early universe and the history of cosmic structure formation. There is also an exotic but scientifically serious possibility called asymmetric dark matter, in which the dark matter abundance is explained by a matter-antimatter asymmetry in the dark sector, analogous to the asymmetry between matter and antimatter in the ordinary sector that left us with a universe full of matter rather than an equal mix of matter and antimatter. If dark matter is asymmetric, it might have interactions that link the dark sector to the visible sector in ways that could be detected in experiments looking for dark matter annihilation products or through other indirect detection techniques. And then there is the possibility, perhaps the most mind-expanding of all, that dark matter is not a single type of particle but a dark sector, an entire zoo of dark particles with their own forces and interactions, analogous to the rich particle content of the standard model. In this scenario, there might be dark photons, dark electrons, dark atomic nuclei, dark chemistry. The dark sector might have its own version of everything we see in the visible world, invisible to us but interacting with itself through dark forces. This is not idle speculation. There are serious theoretical models along these lines, and they have interesting observational consequences. Dark sector particles might interact with ordinary matter through portal forces, tiny couplings between the dark and visible sectors that could be detected in specific experimental configurations. The possibility of a dark sector opens up an even more extraordinary thought. What if dark matter has complexity? What if dark matter can form structures? What if, in some rare cosmic environments, dark matter condenses and interacts with itself strongly enough to form something like dark atoms or dark chemistry? This is far from the mainstream, but some theoretical physicists have explored these ideas seriously. And if such complexity is possible, even in principle, then the universe might be even more interesting than we currently imagine. Of course, We should not let imagination run too far ahead of evidence. The most productive approach is to focus on the testable predictions of specific dark matter models and design experiments to test them. But the broader point is worth making. The discovery of dark matter could open not just a new chapter, but an entirely new book of physics, one that contains characters and plot lines we have not yet imagined. Now let us come back to Earth. Literally. Let us think about what it means for ordinary people, not just physicists, that a dark matter hurricane might be passing through them right now. What does this tell us about our experience of the world and about the limits of human perception? We are accustomed to the idea that our senses are limited. We cannot see ultraviolet or infrared light. We cannot hear ultrasound or infrasound. We cannot feel magnetic fields. We know that the world contains things our senses were not evolved to detect, and we have built instruments to extend our perception into those realms. Cameras and detectors that see invisible light. Microphones that hear inaudible sounds. Magnetometers that measure magnetic fields. But dark matter is different, because it does not interact with any of the forces that underlie our instruments. It does not emit light. It does not emit radio waves. It does not push molecules around in ways we can feel or smell or taste. It is, in the most fundamental sense, beyond our natural perception and beyond most of the instruments we have ever built. The underground detectors searching for dark matter are not just bigger or more sensitive versions of our ordinary perceptual instruments. They are qualitatively different devices, built to probe a realm of nature that is genuinely invisible to everything that came before them. They are the equivalent, for dark matter, of the first telescopes that revealed the telescopic universe that the naked eye could never see, or the first microscopes that revealed the microscopic world of cells and bacteria. They are opening a new window on reality that has been closed since the beginning of human awareness. This is what makes the search for dark matter not just a scientific endeavor, but a genuinely philosophical and even spiritual one. To search for dark matter is to push the boundary of what is perceivable, to assert that reality is larger than what we can directly experience, to build instruments that function as extensions of human consciousness into a previously impenetrable domain. It is an act of intellectual courage, a refusal to accept that the world ends at the boundary of what we can currently detect, a commitment to the idea that the universe has secrets worth finding even if they take generations to uncover. And here is what is perhaps most remarkable. The universe has been telling us about dark matter for as long as galaxies have existed. Every galaxy that spins too fast for its visible mass, every cluster that holds together against physics that says it should fly apart, every gravitational lens that bends light more than it should, every cosmic web that could not have formed without a cold dark matter scaffold. All of these are signals that the universe has been broadcasting constantly for billions of years. We just did not have the tools to receive them until recently, and we still do not have the tools to fully decode the message. But we are working on it. The underground detectors, the quantum sensors, the directional dark matter detectors, all of these are our attempt to build receivers for a signal that has been there all along. The dark matter hurricane is one particularly loud note in that signal. A specific, directional high-velocity stream of ancient dark matter flowing through our solar system right now, pointing back to a dwarf galaxy that was eaten by our own before our sun was born. If we can hear it, if our detectors are sensitive enough to pick up that note above the background noise, then everything changes. Then we have not just detected dark matter. We have read the history of our galaxy in the language of invisible particles. We have completed a circuit between the cosmic and the quantum, between the largest scales of the universe and the smallest. And think about what happens next. Once we know what dark matter is, once we have a confirmed particle or field that we can study, the second phase of dark matter science begins. Instead of asking what is dark matter, we start asking how does dark matter behave. We measure its properties with increasing precision. We study the structure of dark matter halos in detail. We test whether dark matter is truly cold and collisionless, or whether it has self-interactions that produce more complex behavior. We look for dark matter in different environments, in the centers of galaxies where it may be very dense, in dwarf galaxies where it may dominate the dynamics completely, in the early universe where it shaped the formation of the first structures. This second phase of dark matter science would be as scientifically rich as the entire history of particle physics up to now, and it would reshape cosmology, astrophysics, and fundamental physics simultaneously. The dark matter hurricane, passing through our solar system right now, is potentially the key that unlocks this second phase. Before we move toward the final phase of this exploration, let us pause and consider the strange beauty of where we are in history. We are living in a moment when humanity has become sophisticated enough to ask questions that our ancestors could not even formulate, let alone answer. We have built instruments of extraordinary sensitivity to probe realms of nature that are completely invisible to direct human perception. We have theoretical frameworks that extend our reasoning into regimes of energy, distance, and time that are inconceivably remote from everyday experience. And we are using all of these tools to ask the most fundamental question there is: what is the world made of? We are also living in a moment when that question is tantalizingly close to an answer. The evidence for dark matter is overwhelming. The list of possible candidates has been narrowed considerably. The experiments are now sensitive enough to probe the most theoretically motivated regions of parameter space. The astrophysical observations are providing increasingly specific targets and predictions. And the dark matter hurricane, the S1 stream flowing through our solar system, is perhaps the most concrete and specific prediction in the entire history of dark matter research. A stream with a measured direction, a measured speed, a known origin, and calculable implications for multiple different detection experiments. If history is any guide, the next major breakthrough in fundamental physics will come from a direction that surprises us. The breakthroughs always do. The discovery of the cosmic microwave background came from engineers investigating noise in a microwave antenna. The discovery of pulsars came from a graduate student looking at apparently boring data that everyone else had dismissed. The discovery of the acceleration of the universe's expansion came from people trying to measure something completely different. Science at the frontier is full of surprises, and the dark matter story is likely no exception. But the S1 stream represents something important even in the context of that unpredictability. It represents the maturation of dark matter science to the point where astrophysical observations and laboratory experiments are informing each other in real time, where a satellite designed to map star positions can provide crucial input for underground particle physics experiments, where the history of galactic mergers is relevant to the design and operation of quantum sensors. This level of cross-disciplinary integration is a sign of a field that is ready for a breakthrough. Now, let us spend some time with the mathematics, not to overwhelm but to give you a sense of what the numbers actually mean. When physicists talk about dark matter density in the solar neighborhood, they typically express it in units of GeV per cubic centimeter, where GeV is a unit of energy equivalent to about the mass of a proton. The local dark matter density is estimated to be about 0.3 to 0.4 GeV per cubic centimeter. That sounds like a tiny number, and in terms of mass per volume it is roughly equivalent to about 1 proton mass per 5 cubic centimeters, which is far less dense than even the best vacuum achievable in a laboratory. This is why dark matter is so hard to detect. It is not that our detectors are small. It is that even the best natural dark matter density is incredibly dilute. But here is the key. A WIMP or axion detector does not just sample the dark matter at one instant. It sits in the dark matter stream for months or years, accumulating rare events. And the rate of rare events scales with the flux of dark matter particles, which is the density times the velocity. For a stream moving at 470 kilometers per second, the flux is substantially higher than for dark matter moving at typical galactic velocities, which are more like 200 to 300 kilometers per second. This velocity boost increases the detection rate, which is why the S1 stream, even if its local density is similar to the average galactic halo density, can significantly enhance the signal in a detector. The number of dark matter particles passing through a cubic meter of material per second depends on the density and velocity of the stream and on the mass of the individual dark matter particles. For a typical WIMP mass of 100 GeV and a stream density similar to the local galactic halo density, roughly 1 million WIMPs per second pass through a square meter of surface. Most of these pass right through without interacting. But occasionally, very rarely, one of them hits a nucleus. The probability of this interaction, called a cross-section, is the quantity that dark matter experiments are trying to measure. Current experiments can probe cross-sections as small as about 10 to the minus 47 square centimeters, which is almost unimaginably small. To put it in perspective, the nucleus itself is about 10 to the minus 25 square centimeters in cross-section, so the dark matter interaction cross-section is more than 20 orders of magnitude smaller than the nucleus itself. This is the extraordinary challenge of dark matter detection. Not just finding a rare event, but finding an incredibly rare interaction between particles that barely interact at all, in a background of much more common interactions from cosmic rays, radioactivity, and neutrinos, and doing so with enough statistical confidence to make a discovery claim that the scientific community will accept. The experimenters who work on these detectors are, in a very real sense, looking for a whisper in a thunderstorm. And yet they persist. And the detectors get better. And the sensitivity improves. And every year, the region of dark matter parameter space that remains unexplored shrinks. The dark matter hurricane, if it is there, is becoming harder and harder to hide. There is something else worth mentioning here, something that connects the dark matter story to much older human questions about the nature of reality and our ability to know it. Throughout history, humans have repeatedly discovered that the visible world is not the whole story. The development of chemistry in the 17th and 18th centuries revealed that matter is made of elements and molecules, invisible to the naked eye but real. The development of atomic physics in the 20th century revealed that atoms are made of even smaller things, protons and neutrons and electrons, again invisible but real. The development of particle physics revealed that protons and neutrons are made of quarks, particles that cannot even in principle exist in isolation. Each layer of reality that has been revealed has been more surprising, more counterintuitive, and more beautiful than the one before. Dark matter might be the next such revelation. A new layer of reality that is invisible to everything we currently have, but present everywhere, shaping everything, and waiting to be discovered. And when it is discovered, it will not just add a new particle to the list. It will change our understanding of what matter is, of what the universe is made of how cosmic structures form and evolve, of what the first moments of the Big Bang were like. It will be a revelation as profound as any in the history of human thought. You are alive in the moment when that revelation might be approaching. When the instruments are sensitive enough, when the astrophysical targets are specific enough, when the theoretical frameworks are developed enough, that the answer might be just around the corner. Whether it comes from LZ or Xenon NT or ADMX or from a completely unexpected direction, the answer is probably closer than it has ever been. And the dark matter hurricane, streaming through your body right now at 470 kilometers per second, might be the messenger that finally breaks the silence. Let us now talk about what the discovery of the S1 stream means specifically for our understanding of the Milky Way's history, because this is a story that goes beyond dark matter and into the deep history of our cosmic home. The Gaia satellite has been transformative for galactic astronomy in ways that go far beyond the identification of stellar streams. By measuring the positions, distances, and velocities of more than 1 billion stars with unprecedented precision, Gaia has enabled astronomers to reconstruct the Milky Way's assembly history in remarkable detail. Before Gaia, our picture of the galaxy's formation was based primarily on the properties of individual stars and small stellar populations. After Gaia, we can see the entire architecture of the galaxy's history written in the motions of billions of stars. What Gaia has revealed is that the Milky Way has had a complex, violent past. The major Gaia-Sausage-Enceladus merger, which I mentioned earlier, was a collision with a galaxy comparable in mass to the Large Magellanic Cloud, which is itself about 15% the mass of the Milky Way. This merger, which occurred roughly 8 to 10 billion years ago, sent shockwaves through the Milky Way that are still visible in the star-forming history and chemical composition of its stellar populations. The stars from the disrupted galaxy form the interstellar halo, a dynamically distinct population with characteristic elongated orbits that cross the inner parts of the galaxy. The S1 stream represents a much smaller event, a minor merger with a dwarf galaxy of much lower mass. But its identification in Gaia data is significant because it shows that we can now detect and characterize even relatively small merger events from billions of years ago, using the kinematic imprints they leave on the present-day distribution of stars. As Gaia continues to release new data, and as future surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time add even more stars to the catalog, our picture of the Milky Way's merger history will become increasingly complete. And each new merger event that is identified, each new stellar stream that is traced back to its origin, is a potential source of dark matter streams flowing through our solar system. The local dark matter environment is not simple. It is a superposition of many components, each with its own velocity distribution, each carrying the imprint of a different episode in the Milky Way's history. Understanding this complexity is both a challenge for dark matter detection and an extraordinary opportunity for galactic archaeology, the reconstruction of our galaxy's past from the fossil record embedded in present-day stellar motions. Think about what this means for the long-term future of both fields. As dark matter detectors become more sensitive and as astrophysical observations become more detailed, the two fields will become increasingly intertwined. Detections in dark matter experiments will inform models of the galactic dark matter distribution. Models of the galactic dark matter distribution will inform the design and interpretation of dark matter experiments. And stellar streams identified by surveys like Gaia and its successors will provide specific, testable targets for the experiments. It is a virtuous cycle that could accelerate our understanding of both the Milky Way's history and the nature of dark matter simultaneously. This cross-disciplinary synergy is one of the most exciting developments in modern astrophysics and particle physics, and the S1 stream is one of its best current examples. It is also a reminder that major scientific discoveries often come not from a single experiment or a single observation, but from the intersection of multiple independent lines of evidence and inquiry. The dark matter hurricane story is a product of this kind of cross-disciplinary thinking, and whatever answer ultimately emerges from this story is likely to emerge the same way. Now let us think about what has not yet been found, and what that means. The most sensitive dark matter experiments have placed increasingly stringent constraints on WIMP dark matter. For WIMPs in certain mass ranges and with certain interaction strengths, the experiments have excluded the possibility with high statistical confidence. This is not failure, it is progress. Every region of parameter space that is ruled out is a piece of the puzzle, a direction eliminated from the search space. And as the excluded regions grow, the remaining possibilities become more constrained, guiding theorists toward models that can survive the experimental scrutiny. But there is a genuine tension in the field. Some of the most theoretically motivated WIMP models, particularly those arising from minimal supersymmetric extensions of the standard model, have been pushed into uncomfortable corners by the combination of LHC data and direct detection limits. The parameter space that these models can occupy while remaining consistent with all the data is shrinking. Some physicists take this as evidence that supersymmetric WIMPs are not the right answer. Others argue that there is still plenty of room in the parameter space and that the most sensitive future experiments have not yet probed all of it. For axions, the situation is in some ways more optimistic. The theoretical motivation for axions is strong and independent of supersymmetry. The mass range of QCD axions that are cosmologically relevant as dark matter spans several orders of magnitude, and current experiments have only scanned a small fraction of that range. Future axion experiments, using technologies like quantum sensors and resonant cavities coupled to photon counting devices, promise to scan much of the remaining range over the next decade or two. And the S1 stream, with its specific velocity signature, could make the detection of stream axions easier and more distinctive than detecting background halo axions. There is also the exciting possibility that dark matter exists in a mass range that we have barely begun to explore. Ultralight dark matter, also called fuzzy dark matter, consists of particles so light, with masses as small as 10 to the minus 22 electron volts, that quantum mechanical effects are important on astrophysical scales. Such particles would behave as a coherent quantum wave rather than individual particles, forming what is sometimes called a Bose-Einstein condensate on the scale of entire galaxies. Fuzzy dark matter would have distinctive signatures in the structure of dwarf galaxies and in the cosmic microwave background that are different from those of cold dark matter. And it would interact with matter in ways that are amenable to detection by quantum sensors. This is an exciting frontier, and it represents exactly the kind of unexpected dark matter that might have been hiding just beyond our current reach. On the other end of the mass spectrum, there is also interest in macroscopic dark matter. Dark matter made not of individual particles but of larger, composite objects. The most famous example is primordial black holes that formed in the early universe before stars existed, which could make up some or all of the dark matter. Primordial black holes do not interact with light or ordinary matter except through gravity, making them truly dark. They have been constrained by a variety of observations, including gravitational microlensing surveys and the gravitational wave observations from the LIGO and Virgo detectors, but there remain mass windows where they could still make up a significant fraction of the dark matter. This is another reminder that dark matter might not be a single type of thing and that the answer might be complex and multi-component. The breadth of this theoretical landscape reflects the genuine depth of our ignorance about what dark matter is. We know it exists, in the sense that we know its gravitational effects are real. We know roughly how much of it there is. We know roughly how it is distributed in the universe. But we do not know what it is made of. And that gap between gravitational knowledge and particle physics ignorance is one of the great intellectual chasms of our time. Bridging that chasm is the goal of the entire dark matter enterprise. And the dark matter hurricane, the S1 stream flowing through our solar system right now, is one of the most promising bridges we have found. Let us shift our perspective one more time, from the scientific to the personal, and think about what this story means for each of us individually. Because there is something profoundly personal about the idea that you are, right now, immersed in an invisible river of ancient matter, a remnant of a galaxy that was consumed by our own before the Earth was born. We spend our lives in the visible world, navigating the familiar landscape of objects and people and relationships that we can see and touch and measure. We build our understanding of reality on the bedrock of that visible experience. And yet, if the physicists are right, if dark matter is real, and if the S1 stream is flowing through us at this moment, then the reality you inhabit is far larger and stranger than any of your senses can tell you. You are not just in a room, or a city, or a country, or a planet. You are in the middle of a dark matter stream that stretches for thousands of light years, that originated in an ancient galactic catastrophe, that has been flowing through space for billions of years, and that has just happened to be passing through the small region of the galaxy where our solar system currently orbits, in the brief cosmic instant that constitutes the age of human civilization. This does not diminish the visible world. It enriches it. It adds depth and context to everything we experience. The atoms that make up your body were forged in stars and scattered across space by stellar explosions. The planet you stand on was assembled from the debris of an ancient solar nebula. The galaxy you live in was built by the consumption of smaller galaxies over billions of years. And the dark matter flowing through you right now is a remnant of that construction process, a fragment of the building materials that shaped your cosmic neighborhood. You are not separate from this story. You are inside it. And the scientists who are building the detectors and writing the papers and analyzing the data are, in a sense, trying to hear the story that the cosmos is telling through the medium of dark matter. They are trying to decode a message that has been flowing through our solar system for billions of years, written in the velocities of invisible particles. They may not hear it this year or next, but they are listening. And the listening is itself a profound act, an expression of humanity's deepest impulse to understand, to connect, to know. Now let us think about some of the most interesting and unexpected connections that the dark matter hurricane story has revealed. Connections that span disciplines and cross boundaries in ways that are genuinely surprising. One of the most unexpected is the connection between dark matter streaming and the science of gravitational waves. The LIGO and Virgo detectors have opened a new window on the universe by detecting gravitational waves, ripples in space-time caused by the collision of massive objects like black holes and neutron stars. But gravitational waves could in principle also be produced by dark matter processes. particularly if dark matter forms dense objects like primordial black holes or dark stars that can merge and produce detectable gravitational wave signatures. The parameters that LIGO constrains for dark matter black holes overlap with those constrained by direct detection experiments, creating an interesting complementarity between two completely different observational techniques. Another unexpected connection is with neutrino physics. Neutrinos are real, known particles that interact only weakly with ordinary matter, similar in some ways to the proposed WIMP dark matter. The techniques developed for neutrino detectors, deep underground tanks of purified water or liquid scintillator, have significant overlap with the techniques used for WIMP detectors. And the backgrounds that WIMP detectors must understand and control, including neutrinos from the sun and from supernova remnants, are the very signals that neutrino physicists are trying to study. The two fields have developed a rich symbiosis, sharing technologies, personnel, and infrastructure in ways that benefit both. There is also a fascinating connection with the study of stellar structure and evolution. If dark matter particles are captured by stars as they orbit through the galaxy, accumulating over billions of years in stellar interiors, their annihilation or scattering could affect the temperature profile and structure of stars in detectable ways. For the Sun, these effects are small but potentially measurable with the precise helioseismology data available from instruments like the Solar and Heliospheric Observatory. For compact stars like white dwarfs and neutron stars, which are even denser than normal stars and can trap dark matter more efficiently, the effects could be more dramatic. Some theorists have proposed looking for anomalous cooling rates in white dwarfs or anomalous heating rates in neutron stars as signatures of dark matter interactions. These are exotic ideas, but they represent the kind of creative thinking that the dark matter problem inspires. And then there is the connection, perhaps the most personal of all, with the history of our own solar system. The dark matter in our neighborhood has been gravitationally present throughout the entire history of the solar system. Its tidal forces have contributed, at a tiny level, to the dynamics of all the objects in our solar system over its 4.5 billion year history. Its gravitational influence on the Oort cloud, while small, is not zero, and over long timescales it may have had some effect on the flux of comets into the inner solar system. The idea that dark matter has been a silent, invisible participant in the evolution of our solar system, present but undetected, affecting things in subtle ways that we have never been able to attribute to it, is both humbling and fascinating. We are not just observers of the universe from a safe distance. We are embedded in it, shaped by it, made of it, affected by it in ways both visible and invisible. The dark matter hurricane is a reminder of that embeddedness. It is the cosmos reaching into our solar system, into our detectors, into our equations, trying to tell us something about itself. Now let us talk about the future, and about what the next decade or two might bring in the search for dark matter, and specifically in the test of the dark matter hurricane hypothesis. The next generation of WIMP detectors, including the full runs of LUX Zeppelin and Xenon NT and the planned Darwin experiment in Europe with 50 tons of liquid xenon, will probe WIMP masses and cross-sections down to the neutrino floor, the level at which the coherent neutrino scattering background begins to mimic the dark matter signal. If WIMPs exist with masses between about 3 and a few hundred GeV and interaction cross-sections above the neutrino floor, they will almost certainly be detected in the next decade. If the experiments reach the neutrino floor without finding anything, the most natural WIMP candidates, the thermal relic WIMPs predicted by supersymmetry in its simplest forms, will be essentially ruled out, and the field will need to pivot to lighter or more weakly interacting candidates. 4 axions, the ADMX experiment and its successors are expected to scan through the cosmologically motivated axion mass range, roughly from a few microelectron volts to tens of microelectron volts, over the next decade or so. If QCD axions exist in this mass range, they should be detectable, and the quantum sensor experiments targeting ultralight dark matter will probe an entirely new region of parameter space that no previous experiment has been sensitive to. For directional dark matter detection, the path forward is more challenging but also more rewarding. Next-generation directional detectors based on advanced gas-time projection chambers or nuclear track detectors might become sensitive enough to test the S1 stream prediction directly, looking for the excess of events coming from the predicted direction. This would require substantial improvement in target mass and sensitivity, but the technology is advancing and there is strong scientific motivation. And for all these experiments, the astrophysical guidance from Gaia and future surveys continues to improve. Future releases of Gaia data will identify additional stellar streams and better characterize the ones already known, including the S1 stream. The Vera C. Rubin Observatory, which began science operations in 2024, will conduct the deepest and widest photometric survey ever attempted, identifying extremely faint stellar streams that are currently below detection thresholds. The upcoming Nancy Grace Roman Space Telescope will add near-infrared photometry to the mix, enabling the identification of stellar populations that are difficult to study in optical light. And spectroscopic surveys like WEAVE in Europe, for most in Chile, and the Dark Energy Spectroscopic Instrument at Kitt Peak will measure the chemical compositions and precise radial velocities of millions of stars, adding crucial information for the identification and characterization of merger remnants. The picture that emerges from all of this, from the next generation of dark matter experiments and the next generation of galactic surveys operating together, will be transformative. We will have a much more complete picture of the Milky Way's merger history and of the dark matter streams flowing through our solar system. We will have much more sensitive constraints on dark matter properties from multiple different experimental approaches. And we will have, potentially, a detection. If we do find a dark matter signal, and if it has the specific velocity signature predicted by the S1 stream, the celebration in the physics community will be unlike anything since the discovery of the Higgs boson in 2012. And unlike the Higgs, which was predicted theoretically and whose discovery, while thrilling, confirmed what most physicists already expected, a dark matter detection would be truly transformative, opening up a new category of physical reality that we have known exists but never been able to examine directly. The next few years are going to be extraordinarily exciting. The experiments are running. The data is accumulating. The theoretical understanding is deepening. And somewhere in the data, perhaps in a pattern of events at slightly higher energies than expected, perhaps in a narrow peak in an axion spectrum at a specific frequency, perhaps in a directional anisotropy that points toward Boötes, the answer might already be hiding, waiting to be recognized. But let us also be honest about the possibility that the answer continues to elude us. Science does not always deliver on the timescales that scientists hope for or that funding agencies demand. The dark matter problem has already taken longer than many physicists expected. The WIMP miracle, the observation that particles with weak scale masses and interactions naturally produce the right dark matter abundance, led many to expect that WIMPs would be found at the LHC or in first-generation direct detection experiments. That has not happened. The parameter space has not cooperated. And this should be a lesson in humility, both about the difficulty of the problem and about the limits of our theoretical intuition. Dark matter, if it exists as particles, is clearly not in the place where many physicists expected to find it. Either it is lighter or heavier than the naive expectation, or it interacts more weakly, or it interacts through a different channel. Or dark matter is something fundamentally different from what we have been looking for. The silence of the experiments is itself information, and it is information that is pushing theoretical physicists to explore new ideas and new parameter spaces that might not have been considered seriously a decade ago. This is how science progresses. Not always by confirmation, but also by elimination. Not always by finding what you expected, but by being surprised by what you do not find and being forced to think differently. The history of physics is full of cases where the most productive thing an experiment ever did was rule something out, pointing theorists in a new direction that led eventually to the truth. Whatever the truth about dark matter turns out to be, the dark matter hurricane story will remain a beautiful chapter in the history of the search. It represents the moment when galactic astronomy and particle physics came together in a specific, testable, quantitative prediction. When the history of a dwarf galaxy eaten by the Milky Way became relevant to the operation of an underground detector in South Dakota. When the speed of ancient stellar debris flowing through our solar system became a parameter in the design of a microwave cavity experiment. When the cosmos and the laboratory became explicitly, quantitatively connected in a way that they had never been before. That connection is profound, and it is permanent, regardless of whether the dark matter hurricane is ever directly detected. The methodology of using astrophysical structures to inform and guide laboratory searches is here to stay, and it will only become more powerful as our observational and experimental capabilities improve. So let us conclude this particular journey with an image, or rather a series of images, that try to capture the full scale and significance of what we have been exploring. Imagine you are standing in a field at night, away from city lights, looking up at the Milky Way. The band of light stretches across the sky from horizon to horizon, a river of hundreds of billions of stars, the accumulated product of billions of years of cosmic history. Somewhere in that band of light, about 2/3 of the way from the center, is a single point, our Sun. Around it, the Earth orbits, and on the Earth, you stand in your field, looking up. Now imagine you can see dark matter. Not just the stars, but the invisible scaffolding that holds them all together, the vast, roughly spherical halo of dark matter that extends far beyond the visible disk of the galaxy, reaching into intergalactic space, fading slowly into the cosmic web. The halo is not uniform. It is lumpy, streamed, complex, and flowing through the part of the halo where you are standing like a river within a river is the S1 stream, a coherent flow of dark matter particles moving at 470 kilometers per second toward you, through you, past you. These particles are not from here. They were not born in this part of the galaxy. They were part of the dark matter halo of a small galaxy that orbited the Milky Way billions of years ago, drawn in by the gravitational pull of our larger galaxy, stretched and torn and scattered into a stream that has been flowing through space ever since. They have been flowing through this part of the galaxy since before the Earth was born. They will continue flowing long after the Earth is gone. And tonight, in a mine in South Dakota or beneath a mountain in Italy, a tank of liquid xenon sits in the dark, listening for the tap of a particle that barely interacts with anything. Listening for a message from the deep past of the cosmos. Listening for the dark matter hurricane. Whether that message is heard tonight or next year or in a decade, the listening itself is one of the most remarkable things our species has ever done. We are small creatures on a small planet around an ordinary star in an ordinary galaxy. But we have built instruments that can hear cosmic whispers. We have developed theories that can predict invisible streams. We have looked at the motions of stars and deduced the existence of matter that no human eye has ever seen. We have reached out, with our mathematics and our detectors and our curiosity, into the darkness of the unknown universe and said, "We know you are there. We will find you. We will understand you." That is what the dark matter hurricane is. Not just a stream of particles. Not just a physics puzzle. It is an invitation. An invitation from the cosmos to look deeper, to listen harder, to think bigger. It is a reminder that the universe is stranger and richer and more beautiful than we can currently perceive, and that the work of understanding it is one of the most profound things human beings can do. There are few questions in all of science that carry the weight of this one. Few mysteries as deep. Few searches as difficult. And few potential discoveries as transformative. The dark matter hurricane is flowing through you right now. We just have not figured out how to feel it yet. But we are trying. And that trying is everything. Let us now go even deeper into the experimental details and the human stories behind the search, because science is not just equations and graphs. It is people. People who have dedicated their lives to answering questions that may not be answered in their lifetimes. People who work in laboratories carved from bedrock, who live with uncertainty as a daily companion, who check their data 1,000 times before allowing themselves to believe what it might be showing. The search for dark matter is one of the most intensely human enterprises in the history of science, and the S1 stream has given it a new urgency and a new direction. The Sanford Underground Research Facility in Lead, South Dakota, is built in the former Homestake Mine, once the deepest gold mine in North America. The mine was operational from 1876 to 2002 and produced 40 million troy ounces of gold over its lifetime. After it closed, the physicist Ray Davis had already used it for a groundbreaking experiment measuring solar neutrinos, work that eventually earned a Nobel Prize. Today the site hosts the LUX Zeppelin experiment and several other underground physics experiments. The rock above the detector provides a shielding equivalent that reduces cosmic ray muon flux by a factor of more than 1,000,000 compared to the surface. The physicists who work at the Sanford facility spend weeks at a time underground. They navigate narrow tunnels carved from hard rock, take elevators that descend more than a mile into the earth, and work in laboratory spaces that must be kept extraordinarily clean to prevent radioactive contamination of the detectors. The environment is alien, far from sunlight, far from the ordinary rhythms of surface life. And yet the work they are doing there is pointed at the cosmos, at galactic scales and cosmic timescales, at a stream of dark matter that began as the halo of an ancient dwarf galaxy and has been flowing through space ever since. There is a beautiful paradox in this. To find the most cosmic thing imaginable, a relic of galactic history flowing through our solar system from billions of years ago, you have to go underground. You have to shield yourself from the universe's ordinary radiation to hear the extraordinary signal. You have to go deeper into the earth to reach farther into the cosmos. The underground laboratory is a kind of listening chamber, a place where the noise of the ordinary world is reduced enough that the whisper of the extraordinary might be heard. The scientists at these facilities are extraordinarily dedicated. Many of them spent years or decades working on experiments that produced no dark matter signal. They have learned to find satisfaction in the constraints they set, in the parameter space they eliminate, in the techniques they develop for the next generation of experiments. They talk about their work with a mixture of scientific precision and genuine passion that is inspiring to witness. When you ask them about the possibility of a dark matter hurricane flowing through their detector, they become animated in a way that reveals how deeply the search matters to them. Anna, a physicist working on a directional dark matter experiment, once described it this way in an interview published in a popular science outlet. She said that every time she looks at the sky and identifies the constellation Boötes, the direction from which the S1 stream is arriving, she feels a connection between what she is doing in the laboratory and the vast cosmic context it exists in. She said that knowing there is a specific direction, a specific speed, a specific predicted signature, makes the search feel more like a hunt and less like a gamble. And she said that even if her experiment does not detect anything, the limits it places will tell us something real about the universe, and that is always worth doing. This sentiment is common among dark matter experimenters. The culture of the field is one of patient, rigorous, long-term commitment to a question that may take generations to answer. And it is a culture that has been energized by the discovery of the S1 stream and by the broader revolution in galactic archaeology enabled by Gaia. For the first time, the dark matter search has a specific astrophysical target, a cosmic address that can be looked up and compared against what the detectors are seeing. Let us also spend a moment on the theoretical side of the story, because the theorists who predicted what the S1 stream would mean for dark matter detection are as central to this story as the experimenters who are testing those predictions. Kieran O'Hare, then a postdoctoral researcher and now a faculty member, and his collaborators Christopher McCabe and others, did the detailed calculation that connected the stellar stream observations to laboratory predictions. Their work required combining observational data from Gaia, simulations of galaxy formation, and detailed knowledge of multiple different dark matter detection techniques into a coherent analysis. It is exactly the kind of cross-disciplinary work that is increasingly important at the frontiers of physics. O'Hare has been quoted as saying that the S1 stream is particularly exciting because it has a high velocity compared to the typical dark matter halo velocity, which means it could extend the sensitivity of existing experiments to higher energy dark matter interactions that would otherwise be below the detection threshold. He has also emphasized that the stream is not just relevant for WIMPs but has interesting implications for a wide range of dark matter candidates, including axions and other light bosons. What is particularly remarkable about the O'Hare et al. Paper is how it demonstrated that a seemingly unrelated observational result, the identification of a stellar stream by an astrometry satellite, could have immediate and quantitative implications for multiple different particle physics experiments. This kind of unexpected connection is the hallmark of deep scientific insights. It reveals that nature is more interconnected than we often appreciate, that the boundaries between scientific disciplines are artificial constructs that the universe does not respect. The paper has been cited extensively since its publication, spawning a literature of follow-up studies that have refined the estimates of the stream's dark matter content, explored its implications for specific experimental configurations, and extended the analysis to other stellar streams. It has become a touchstone in the dark matter field, a reminder that astrophysical observations are not just scenic backdrop for particle physics but can be crucial inputs that guide the search. There is also a theoretical angle that deserves more attention, which concerns the question of how the dark matter in the S1 stream relates to the dark matter that is normally assumed in detector analyses. Most dark matter experiments assume a standard halo model for the local dark matter distribution, which treats the dark matter as a smooth, isotropic, Maxwellian velocity distribution. This is a simplification, and it is known to be inaccurate at some level, but it has been the standard assumption because it is tractable and because the deviations from it were believed to be small. The S1 stream is a deviation from the standard halo model that is not small. Its contribution to the local dark matter flux at certain velocities could be comparable to or larger than the smooth halo contribution at those velocities, particularly if we are near the peak of the stream's local dark matter density. This means that the standard halo model is potentially a poor approximation for interpreting the results of dark matter experiments, and that more realistic, empirically motivated models of the local dark matter distribution are needed. This is a practical issue with direct consequences for how experimental results are interpreted. If a detector sees an excess of events at high energies, the significance of that excess and its interpretation in terms of dark matter properties depend on what you assume the dark matter velocity distribution looks like. If you use the standard halo model, you get one answer. If you use a model that includes the S1 stream, you might get a different answer. And the difference could matter for deciding whether a signal is real and for determining what dark matter model it is consistent with. This has motivated a body of work on what is called the halo-independent analysis of direct detection data, which attempts to make statements about dark matter that are independent of assumptions about the velocity distribution. These analyses are more complex but more robust, and they are becoming increasingly important as experiments become more sensitive and the need for accurate backgrounds and signal models grows. The broader lesson here is that understanding the local dark matter environment, including the presence of streams like S1, is not just a matter of astrophysical curiosity. It is essential for correctly interpreting the results of dark matter experiments. The experiment and the astrophysics are inseparable. You cannot do one correctly without doing the other. Let us now zoom all the way out and think about the biggest picture of all. What does the dark matter hurricane tell us about our place in the universe, about the relationship between the visible and invisible worlds, about the nature of knowledge itself? Science has a long history of revealing that the visible world is embedded in something larger and more complex that the senses cannot directly perceive. Newton showed that the apple falling from a tree and the moon orbiting the Earth are governed by the same force, a force that is invisible but whose effects are everywhere. Maxwell showed that light is a wave in an electromagnetic field that pervades all of space. Einstein showed that space and time are not fixed backgrounds but dynamic entities that curve in the presence of mass and energy. Quantum mechanics showed that the behavior of matter at small scales is governed by a mathematical structure, the wave function, that has no direct physical interpretation but correctly predicts all observations. Dark matter would be the next step in this sequence. The discovery that visible matter is embedded in a vast, invisible sea of dark matter would reveal another layer of the universe that our senses cannot directly perceive, another set of forces and structures and dynamics that have been operating all along, shaping everything we can see. And the dark matter hurricane, a specific stream of invisible particles flowing through our solar system right now, would be the first time we could say, here is where the invisible world and the visible world explicitly intersect in a specific place, at a specific time, with specific measurable properties. This would be more than a scientific discovery. It would be a revelation about the nature of reality. It would change what we mean when we say we understand where we are and what we are made of. It would open a new chapter in humanity's ongoing effort to know the universe it inhabits. And that is why the dark matter hurricane is one of the most extraordinary ideas in contemporary science. Not just because it is good physics, though it is. Not just because it has testable predictions, though it does. But because it connects the deepest questions about the nature of matter and energy to the specific, concrete reality of our solar system and our galaxy. It makes the abstract tangible. It makes the cosmic local. It makes the invisible, however briefly and approximately, visible. The storm is passing through you right now. You cannot feel it. You cannot see it. But it is there, if the physics is right, streaming through your cells and your bones and the air around you, carrying the memory of a galaxy that died before the Earth was born, flowing toward whatever future the universe has in store, indifferent to our questions but perhaps not entirely beyond our ability to hear. Listen. The universe is trying to tell you something, and we are slowly, with great effort and great patience and great care, beginning to understand the words. The search for dark matter is the search for the rest of reality, and the dark matter hurricane is the place where that search has become most concrete, most directional, most specific. It is the moment when the invisible storm and the human instrument have come closest to each other, when the gap between what we know and what exists is most nearly bridgeable.